Hi guys, my name is Radoslav and today I'm going to be explaining the solution to one of the problems from the recent long challenge, like the December long challenge. And yeah, you can see a small slide about me, and I guess let's just go to the problem. I'm going to be explaining the hardest problem, which was called Palindromic Equivalence, or PALINDEQ. And it was, as I said, the hardest problem, and it required some pretty complicated topics like Chordal graphs. And yeah, I guess let's first start with the problem statement. This time I'm actually gonna try making the video shorter because that was some of the feedback we received. So yeah, I'm gonna try keeping the solution on a higher level and not so much into the small details. So yeah, I guess let's go to the problem statement. All right, so basically in the problem, we are first given the definition of palindromic equivalence. And in some sense, two strings will be palindromically equivalent if and only if for every two integers such that the first one is less than or equal to the second one, like the two integers are left and right, or in other words, this is like a substring. Basically, we want the substring from left to right of the first string to be a palindrome if and only if the substring from the same given by the same range of the second string is also a palindrome. In other words, like two substrings are palindromically equivalent. First, if they have the same length, and secondly, if for every subrange, they're like n choose two subranges, one of the strings is a palindrome if and only if the second one is a palindrome, and vice versa. Like if the second one isn't a palindrome, then the first one also shouldn't be a palindrome. And yeah, basically this is like the palindromic equivalence. And now the problem is that we are basically given some string s, like s is given to us, and we want to find the number of subset p, basically p is the subset, of the integers from 1 to n. This subset will basically represent the positions in our string, and we want to find the number of ways to create, basically the number of ways to choose a subset such that there will be some string x such that all of the positions in this subset p will be equal. In other words, we want to find the number of subsets of positions such that there exists some string x that's equivalent to our string s was given to us, such that the positions of x on all of these positions p are equal. In a way, that's pretty complicated, so I advise you to stop the video to actually understand what this definition says. But further on in the problem, we will actually show what this definition actually means. And yeah. Also, as the answer is pretty large, we need to output it modulo a very large number. And yeah, basically that's overall the problem statement. And the constraints are basically n up to 2000. So in a way, like you required a quadratic solution. There was like a small subtask, which is like with n less than 10. So yeah, here you could basically do some brute force. In a way, like you basically need to understand what the definition what the definition means. Like you just implement all possible subsets and you just brute force, check the equivalence with a brute force. But yeah, like we are mostly going to focus on the large solution because that's the hardest problem, and the people who are watching it probably will already know how to write the brute force. Okay, let's go back to the problem statement. I'm going to explain it in three parts. The first one will be the reduction. Then the second one will be the main observation. To be completely fair, I already basically said what the solution will be. As after you realize that the problem is related to chordal graphs, and also after the reduction to a graph problem, although the reduction is a bit, maybe not the most obvious thing, but it's quite trivial. But like after you realize and prove that the graph will be chordal, then the algorithm is, I mean, it's basically, yeah, you'll actually see. And yeah, the hard part, in my opinion, of this problem was to actually realize that the graph was chordal. because after that you can, in a way, easily solve it if you have actually solved some past problems about Chordal graphs, or if you just know what a Chordal graph is. But yeah, I guess let's just go straight to the point. Basically, let's start with the reduction. I'm going to use this definition throughout the whole presentation. It will be basically P of I and j for some I less than or equal to j will basically mean whether the substring from I to j is a palindrome. In other words, like, that's basically one of the most obvious precomputes you can do in this problem, and it's like just for every range, whether it's palindrome or not, in S, I mean. So in other words, like, this thing will be true if and only if this S from I to j will be a palindrome. And the first part of the reduction is the following. We know that if P of ij is a palindrome, then we want the x from I to j. Basically, like, we want x from position I to position j to also be a palindrome. Or in other words, we want the following condition to be true, like L here is the length, and yeah, we basically want this substring to, yeah, we want this condition to hold. So yeah, basically we can also reduce this condition, because in a way, like, we want this thing to be true, like the above condition, we want it to be true for all of the, yeah, let me also put the thing, the pointer. So yeah, we basically want the following thing to be true for all I and j, but yeah, we can easily reduce it, because if this is true, then we can just explicitly use that if P of ij is true, then the leftmost character should be equal to the rightmost character. Why is this true? Well, mainly because if Pij is a palindrome, then also Pi plus 1, Gi minus 1 will be a palindrome, just by the properties of something being a palindrome. So we'll implicitly have the other characters here from the above condition from some other P of ij for some other ij. So in other words, like, we basically, this is basically one of our transformations or our rules we want to have for x, that if P of ij is true, then we know that certainly xi will be equal to xj. Remember that x is the string we actually want to see whether it exists. And like, if we have something like that for s, then we know that this should be true just always. And yeah, that's like the first very basic observation, and we are gonna use it for later on. And now the second observation, which is in a way pretty similar. Imagine that actually P of I plus 1 and j minus 1 wasn't a palindrome, was a palindrome. However, P of ij was a palindrome. In other words, we basically just have a very large string such that the left bound isn't equal to the right bound, but everything in between is a palindrome. And yeah, if we have something like that, then we can also see that the left character shouldn't be equal to the right character. Like, this should be just, I mean, basically the information on the left-hand side can be easily found just by the given string s, and it's not conditioned on anything. So basically, in a way, we can easily find, I mean, we basically just have the information on the left, and in a way, like, we can just infer something about the x. And like, we basically can, if we have the following condition, we can basically infer that xi won't be equal to xj. Like, just basically this will be true always if the left-hand side, if the left-hand side holds for some ij, then the right-hand side will also be true, regardless of the choice of x. So yeah, that's the second part of the reduction. And now let's see how we can actually convert our problem to a graph problem. Basically, let's just create a graph where every vertex will be a position. And initially we have no edges in the graph, so basically we have just n nodes, where, yeah, the position I corresponds to vertex I. Now step 2 will basically be to actually use our first rules, which were like, if we have Pij, then xi will be equal to xj. So in other words, like, we know that the characters at position I and position j will always be the same. So in a way, like, we can basically just merge their vertices. So yeah, in a way, like, that's just one union find or just one DFS. We just have like those rules, and using them, we basically just merge some larger components. And we will basically know that the large components will correspond to the same letter or character. In other words, like actually in the graph, every vertex will represent a certain letter. Maybe some letters can be repeated, but like when we merge a vertex, then all positions that correspond to this vertex will have the same letter or character. But yeah, that's pretty much it. I mean, like, it's kind of obvious that if we have like a rule that something should be equal to something else, we can build the connected components by merging the vertices or something like that. That's like the trivial part of it. And now what about the other edges? Well, if we actually have a rule that's for non-palindromes, or in a way like if we know that two characters won't be equal, we'll actually add an edge between these vertices. Like we'll find the corresponding vertex to I and the corresponding vertex to J. This will be after we have already merged all equal vertices. So anyway, we are going to consider those rules only after we have basically just finished with the previous ones. And yeah, when we have such rules, which are like something isn't equal to something else, we are simply going to place an edge between the vertices corresponding to those two positions. And now, basically, we have built a graph where some of the vertices, initially vertices which were positions in a way, were compressed into some new ones. And now we have edges whenever two vertices can be equal to the same letter. And well, now the problem is actually this new thing, which is we're given a graph, the one we just built, and now our answer to like the final problem is actually the number of independent sets. And this may sound kind of weird if you didn't really understand the definition of S, but this is the way you should start a problem, because else it's very hard to actually approach it. But yeah, if you actually find this thing, then it actually simplifies itself quite a lot. So actually, why is it true? A very simple observation would be like, we basically wanted to find the number of sets. This is basically the definition in the slides. And I guess you have already read or stopped the video here if you didn't really understand what the definition of... Basically, if you haven't really understood what we are searching for in this problem, then just stop the video here and think about it. And we can actually use the bijection that X... Basically, like, we are going to choose this character, this position P, to be equal to the character. Or in other words, like, P is going to be in our set P, like in the large set, or in the subset, if and only if P is actually in the independent set. And you can actually see why is this correct. Well, the independent set won't share any edges between... for the independent set, for every edge, we won't have both its endpoints in the subset. So in the independent set. So in other words, like, we won't really, if we go back to our problem, then we won't really have an edge between two vertices in our set. And basically the edges are the problem, because in a way, like, if we have, in our problem, the edges represent when we have two vertices that can't have the same letter assigned to them. Well, yeah, I mean, basically here why the bijection is pretty clear here. And yeah, then it will be equivalent if we count the independent sets or if we count the first part. So yeah, that's pretty much the first part of the reduction. And yeah, I mean, now we basically have this problem, which is given a graph and find the number of independent sets. Okay, so I guess let's continue to actually the main observation, I would say, which is about this graph. And yeah, it's actually a Chordal graph. Again, if you're not familiar with Chordal graphs, go to Wikipedia. I have linked the page here. It's just read a bit about them, because you won't really get the solution if you are unfamiliar with them. But in a way, they just represent I mean, if you have some cycle of length more than 3, like of length 4 or more, then you're sure that there will be some chord between two of the vertices that don't already have an edge between them. So in other words, the whole graph will look like a bunch of triangles that are like just connected to each other. And yeah, I mean, like, if you think about it, chordal graphs are easier to argue about. And yeah, I definitely advise you to stop the video and check out the Wikipedia page. As I'm trying to keep the video shorter this time, I won't go into details about more about chordal graphs, but yeah, they're a pretty cool construction. There's some exponential algorithms, like some NP problems can be solved in polynomial time on chordal graphs. For example, like actually graph coloring is one example of an algorithm that can be solved in polynomial time for chordal graphs. And yeah, like coloring is one example. Then, as you already guessed, independent set is also another example, because like we are basically solving it right now. And yeah, there are some other examples. Yeah, I advise you check it out because it's a pretty cool concept. But without further ado, let's actually see why our graph is a chordal graph. All right, let's first consider some free positions in the initial string. And like, we are going to consider such positions that we are going to have an edge between L and R and L prime. And by an edge, I mean edge between the vertices. Or in other words, like this string inside of, like basically from L plus 1 to R minus 1, basically this thing inside is a palindrome, but the character at position L prime isn't equal to R. And similarly, the character at position L isn't equal to the character at position R. However, the thing inside is a palindrome. And then this means that we'll basically have an edge from L to R and from L prime to R. And we have assumed that L prime isn't equal to L, because like in a way we want to have two edges. To prove that our graph is actually chordal, we want to show that we'll always have an edge between L and L prime too. Because in other words, like we want to show that we'll also have this edge between those two. So yeah, in a way, let's actually show this thing. So let's first consider the one case where L prime is greater than mid, where mid is actually the middle of the range from L to R. Or in other words, it's basically just L plus R over 2. And now that we have the middle, what we want to actually, we basically want to show that if we have the edge from L prime to R and the edge from L to R, then we'll certainly also have the edge from L prime to L. And what we are going to do is we are basically just going to find the symmetry at the middle of L prime, and we'll call this vertex L second. And what we can actually prove is that L second and L prime will actually represent the same vertex. This is because we did the centering in the middle of the large palindrome, which means that this string from L second plus 1 to L prime minus 1 is also a palindrome, because it's centered again at mid and it has the same number of characters to the left and to the right. And also, because it's a palindrome, the whole thing actually from L prime to from L second to L prime is a palindrome, because like we have the whole string is a palindrome. Therefore, we know that this thing is a palindrome, and we are going to use our first rule from which we inferred some facts about X, which is if we have a palindrome for some range, if some subrange is a palindrome, then the left point will be equal to the right point in X. So in a way, we know that these two positions will be compressed to the same vertex. And now the second fact is basically, we knew that we had an edge from L prime to R, which means that the inner part from L prime plus 1 to R minus 1, so yeah, basically this thing I'm covering above, will be a palindrome. But we also know that the whole string is a palindrome. Therefore, also the first couple of characters will be a palindrome. This is because we actually know that some suffix is a palindrome and the whole thing is a palindrome. Therefore, clearly the prefix of the same length will also be a palindrome. But then this means that we have a palindrome between L and L second, but we also know that L second corresponds to the same vertex as L prime. So this means that if L isn't equal to L second, then we have an edge here. So in other words, if L prime isn't equal to L, we have an edge from L to L second, but L second corresponds to the same vertex as L prime. Therefore, we just have an edge from L to L prime. And in the other case, if L is equal to L second, then we know that L is equal to L second, and L second is equal to L prime, therefore L prime is equal to L. But wait, this actually means that our assumption was wrong, because we assumed that the L and L prime correspond to different vertices. Because we wanted, in the previous case, to actually have two chords. And I mean, like, in this case, we simply will have just one chord. Not chord, we wanted to have, yeah, pardon me, we wanted to have two edges. And like, if L is equal to L prime, then we just have one edge. And if it's this isn't the case, we basically have an edge from L to L prime, which actually means that we have a cycle of length 3. And I mean, using this rule, we immediately get why our graph should be Chordal. And yeah, that's basically the first case. And now the second case is very similar, but we know that L prime will be less than middle. And now we basically use a very similar symmetry. We know that the whole thing from the start to the beginning, from the beginning to the right -1 is a palindrome. Therefore, we know that the thing from L plus 1 to L second -1, so basically this string, is also a palindrome. Again, L second is based on the symmetry using middle. However, this time L prime is on the left. And I mean, clearly L prime and L second will again represent the same vertex, because we have a symmetry at position middle, so these two vertices are symmetrical, so they will represent the same thing. And then what we can see is that, alright, we basically just have absolutely the same thing, but the symmetry is on the other side. So yeah, in a way we will either have an edge from L to L prime, or our assumption would have been wrong, that L is equal to L prime. Because in a way, like, we can assume that L isn't equal to L prime, because if this was the case, we would get contradiction. And yeah, basically we just proved that our graph is a Chordal graph. And I guess when you actually solve the problem, the best way to approach this is to actually try going from position 1 to position n and seeing what our edges will actually look like. And you can actually kind of see that we never... I mean, I think this observation can be found during the contest, and if you actually, in a way, like, just draw it, you would see how it looks. You have like an L, you have an L prime, and you know that if you have this large chord, then you will definitely have this small one. I mean, like, if you have this large chord and this large edge, and also this edge, then you'll definitely also have this edge. And yeah, I mean, basically this is the main observation, and now how can we use it? I mean, our problem basically becomes, we are given a Chordal graph with number of edges equal to n squared, because that's the worst case. Although actually it's... No, we actually can have... yeah, I mean, we can have an edge for every position. Yeah, I mean, like, it's of n squared, although it's way less. And yeah, the number of vertices is at most n. And we want to find the number of independent sets in it. And it actually turns out that this problem is pretty standard. You can actually just Google it. And I mean, like, to be completely fair, if you actually figure out that the graph is Chordal, you can basically just look at the Wikipedia page and go through the papers that are linked in the bottom of the page. But there's an algorithm from 2007, which is basically counting the number of independent sets in Chordal, and it's by Okamoto et al. And yeah, you can find it here. I'm gonna put the link, which basically explains a linear solution for finding Chordal graphs for a given graph. So in other words, it's like linear in the number of vertices and the number of edges. And I'm gonna explain it on a high level. So basically, first we compute the click tree. And again, I already mentioned that Chord graphs are a pretty cool concept, and we can actually argue about them more easily because of those small triangles. Because like they technically represent a clique of size 3. In a way, like we actually, if we just compress the cliques, like the maximal cliques we can find into some new vertices, then we'll actually have a tree from this maximal cliques. You can actually go to the paper because this concept isn't very easy to explain, and I want to keep the video short. So yeah, I mean, to be completely fair, the solution isn't so hard, but I would definitely advise to simply just open the paper, and it's, I mean, the definition of click trees is pretty simple. And after that, there's like a linear DP. However, if you actually try solving this problem by yourself, completely by yourself, without Googling anything, I guess you can basically just compress these components. I mean, basically, whenever we have a cycle, we know that inside of the cycle, we'll basically just decompose it into small cliques of size 3. And those will be our new vertices of our click tree. And yeah, I mean, like, after you create the click tree, there is this dynamic programming which runs in linear time. However, there is actually a simpler solution, which is fast enough, mainly because you can notice that in the click tree, we can have at most, I mean, like, the most straightforward way to do this 3DP after you have built the click tree is to basically just have a solution which is in complexity 2 to the power of number of children. And this is like basically we consider every subset of children, and I mean like whether we are gonna choose the top thing of every child in the edge. I mean like we do the 3DP, and now we have some child cliques, and what we basically do is simply try all possible subsets. I mean, whether we are gonna choose the top thing or not. And I mean, this is actually pretty easy to do, mostly because it turns out that the number of children in the worst case is pretty small. You can actually see that using a similar argument as the one which we used to prove this thing, that the children will be relatively small. So like we will have around a logarithm of n number of children in the worst case. And this means that 2 to the power of children will actually be 2 to the power of log n. So this will actually be n. And this is actually pretty cool because then the whole algorithm won't be, here we won't really have a v, but we will actually have an n times n. I mean, because like for every vertex, we actually go through 2 times log v, so it's like v squared. And I mean, we know that the order of the number of edges is the same as v squared, and that's enough. So like actually we can simplify this paper, and yeah, I mean, you still have to compress those components, which, I mean, basically the components which are in a way like the cycles. And after like you compose all of the cycles, obviously you'll have a tree because, yeah, I mean, that's in a way not really a corner case, but like, yeah, it's very similar to just be connected components, because after you compress those cycles, which in this case are actually cliques, you'll end up without cycles, and the whole thing will actually be a clique. And yeah, the simplest way to do it is after that to basically just have a 2 to the power of children dp. And yeah, compressing this in the most stupid way is again v plus e. I mean, that's not the most stupid way, but like the stupidest way is v squared. So this is again fine. I mean, you just want to compress the cliques in some way, and after that you can just like use either I mean, because objectively most people will probably, because it's a long contest, most people most likely see they can actually Google the solution, so it's fine because it's a hard problem and it's a pretty hard concept. but also you can actually figure out the solution, which is like 2 to the power of children. For example, when I looked at the problems, I first came up with the 2 to the power of children solution, and I didn't really realize that there was this completely linear solution. But yeah, it was also pretty cool. But yeah, in general, the cool part about the problem is basically to actually prove that the graph is Chordal. I mean, not to prove it, but like to actually realize that the graph is Chordal. And after that, it's in a way like if you're familiar with Chordal graphs, most likely you're gonna solve it, because compressing into a click tree is something that, I mean, it's not very common, but it exists in some other problems. And after that, you can just do the DP. And if you're familiar with how like click trees and like Chordal graphs, most likely you're gonna come up with the 2 to the power of children solution. And yeah, I mean, maybe you won't immediately realize why the children are of magnitude logarithm of n, but yeah, you can. One way to think about it is to actually see some corner sample, like not some counter sample, but like try constructing the worst case for the solution, and you realize that to construct it, if you want to construct it, you want to, in a way, like to construct something that increases the maximal children by 1, then you want the whole graph to, I mean, you would have to double the n. And yeah, from this you immediately get that the children will have a magnitude of logarithm. But yeah, overall, that's the problem. And yeah, I mean, it was the hardest problem. I mean, I enjoyed the part of actually reducing it and going to the Chordal version and the independent set. And after that, it's mainly just some work on Chordal graphs. And I guess, like, yeah, you have to be familiar with them to be able to solve it. But yeah, in general, I advise you to check the paper. It's written in a pretty good way. It won't take you a lot of time, but I don't want to focus on it here because, I mean, basically the DP is also not that hard. I mean, it just reduces this 2 to the power of children DP to an additional state, which is basically just the state of the last child. And I mean, like, in a way, you don't really need to go through all the bit masses of the children. You can in a way just combine I mean, you can basically just combine the root with the first child to something new, and then this new thing with the next child, and so on and so on. And in this way, you just need to keep 4 dimensions here, and yeah, this way you'd get something like 4v, which it isn't very hard. So yeah, I advise you check the paper. It's very well written there, and yeah, that was pretty much it. I hope this time I kept the solution pretty fast and I went to the point faster. So yeah.